Hello, everyone. Good morning, good afternoon, good evening, depending where you are. My name is Moin Ahmadipour, and I'm product manager for the S-Frame suite. And today's session is focused on what's new in the upcoming 2022.3 version of S-Frame suite. So today, I'm joined by two other of my colleagues, Siri Sasibot, software developer and product manager for steel design solutions within the S-Frame suite, as well as Chris Brown, senior director and product manager for concrete design solutions in the suite. So today I will start with presenting the new features which are common between the programs within the S-Frame suite first, and then I will be talking about the new features in S-Timber. Then Siri will lead the presentation and we'll talk about the new features in our steel design solutions. And then Chris will take the lead and talk about the new features in the concrete design solutions within the suite. So now starting with what are the new features and in common between all the programs in this upcoming version. So in this upcoming V 2022.3, we are offering named user licensing, which is a new licensing model for the suite. And this type will be available in hosted or managed format only. And certain application bundles are offered within this licensing model. That includes standard edition of S-Frame, S-Concrete, S-Pad, S-Foundation, and S-Timber. And along with the rest of the simulation products, the S-Frame suite is also support for Windows 11 in this upcoming version as well. So now moving on to S-Timber. What's new in S-Timber? So the first feature that I'm going to talk about is the ability to save load case and load combination data as database files. So this enables the user to save the load combination and load cases as a database file, export them as a database, and then import them back into the model or reuse across different projects or share with colleagues. So for demonstration of this feature, I'd like to show this model in which I have quite a few load cases and load combinations. If we take a look at the load cases in this model, there are 6 of them in the model. And then in the load combinations, I have 33 load combinations in this model, and you can imagine it would have been hard to define all these load combinations from scratch in every single project. Now, what we have made possible is this import and export option here. So you can actually go ahead and export to a database file. And then the user is presented with the directory path that this database is saved in. So now, in this case, this database file is created for the user. And now, in order to import them back, I'm using a blank model now. If I look at my load cases, there is none. There's no load combinations in this model either at this time. But I can go ahead and use the import option. So S-Timber defaults to the default directory path for databases, and it already knows my database file, but you always have the option to go ahead and browse to any other path. Now I can select all these load case or combinations, or I can use a subset. I can review them before I import them into my model. I can make any changes if I want to. And then I can see that everything is now imported into my model properly. So what's important here is that load combinations have load cases associated with them. And in this case, all the load cases are also imported for me. So the next feature that I'm going to talk about is design groups for members. So traditionally, it's been possible to assign sections and materials to members one by one and individually. So in this version, we've made it possible to make groups for members and assign the section and material property to that group instead of each member individually. And then all the members in that group will follow that same material and section properties. And this will be helping the design process later on. and it will lead to a more efficient construction schedule. So I want to use this model to present this feature. So you can see in this model, there are many frames as well as many roof beams, as you can notice. And as you can predict, we don't really want these beams to follow different design procedures. So we would like all these members to have the same material and section assignments, especially during the design process. So what I can do, I can go ahead and define my design groups here. One necessity to design groups is having section lists first. It basically means that we create a list of desired sections that we would like to be considered for the design group. So now in this case, I want to go ahead and create a design group section list for myself. And now I can go ahead and select the desired members. I'm just randomly selecting a couple here. Now that I have a section list, I can go ahead and define my design group. I can give it a name. I can define the type that I want my members to have. Then the material, the section list that I just created, and I can assign an initial section to these members as well. So now if I click OK, I need to go ahead and assign the members I want to this group. So I'm selecting all of my members here, and I can choose the roof beam design group for all these members. Now, as you can notice, all these members now follow the same section and material properties. So the next feature is actually member design for timber and steel elements. As timber has had the capability to perform code checks as per timber and steel design codes. And what that means is you can go ahead and analyze your structure, see the demands and the forces in your structure, and review if your members meet code requirements. Now, in this version, we've automated the design process, which comes next, which means that if your member is under-designed or over-designed, it is an iterative process in order to go ahead and find a more suitable section that meets code requirements. And STimber now automatically goes and finds these sections, and it automatically assigns the sections to the members in question. So one necessity to this feature was section list and design groups that I already explained. And there is a sorting and selection criteria that can be defined for the selection process as well. So now I have a short video to showcase this feature. So I have a hybrid model that has steel and timber members in it. I have 3 load cases in this model, as well as 2 load combinations, which will play a part in the design process. Now, I'd like to have a look at the section list and the design groups as well here. So this is basically the list of sections that we want to be considered or studied in the design process. And I've already assigned design groups to my steel, timber, and other members in the model as well. So now, if we want to have an idea of code performance of the members, we can run a code check before the design to see if the members are failing or passing. I'm focusing on the timber members here, and if you can notice, some of the members are failing their checks. Now, I'd like to go ahead and run the design for the timber members. And the design will be performed for each design group, and the results are presented in a spreadsheet format. So now you can see that the suggested design section is actually given to me. And in addition, it's given to me a list of all other acceptable sections within my section list as well. So it is possible to, oops, sorry. it is possible to use the suggested design section that STimber suggests, or go ahead and override the design section with other acceptable sections as well. Now, the next step is to swap the original members with the design sections if we want. We can do that using the run command. A short summary will be presented to us. Now I can go ahead and code check again in order to review my code performance results. And now we can notice that every member is now passing. So the next feature is automatic generation of load response curves for response spectrum analysis as per the latest National Building Code of Canada. So response spectrum analysis is basically an estimation of maximum responses of a structure during an earthquake. Building codes have different design instructions, and they give instructions on creation of the loading functions. And we have now automated this process for different design codes in STimber. So I want to use this model to showcase this feature. If I want to perform a response spectrum analysis, I need to go ahead and create a response spectrum load curve or load case. And if we notice, in the response spectrum load case, I need to have loading curves assigned to my load case, which I don't have yet. So I cancel out of this. I go to my loading functions from the define menu, and then spectral acceleration functions. Now, if I add a new load curve, basically I have the option to input the data manually, which I don't want to do right now. I also have the option to import from a previously saved database, which is very handy. But really what I'm focusing today is automatic generation of this load case as per different building codes. So I can go ahead and define a new record here. I enable the automatic generation, and using that, I can select which building code I want to use. And NBCC 2020 is what's new in this upcoming version. Then if I specify the coefficients for that building code requirement, every data for me will be generated, and the curve will automatically be generated for me as well. Now, if I go back to my load case definition, I have the curve available to me, and I can go ahead and define that curve now. I had a short video that I will skip here. So the next feature is connection design checks and connectors. So in the previous version of STimber with 2022.2, we introduced a basic capability of defining connections between members, which lets the user find the connection design forces after the analysis. Now we've made it possible to define connectors in the model and assign connectors to the connection components, so that we can perform a code check process here as well. So the connectors can be user-defined. All the details can be entered by the user. They can come from a connector database that's shipped with the program, or they can be created by the user as CSV databases, which is understandable by STimber as well. So I want to use this model to showcase this feature. This is a 4-story building that I'm working with. And there are 3 load cases, dead, live, and snow, as well as 2 load combinations, which are our main focus for the connection design here. I want to isolate one frame and assign a connection component between 2 members here. I want to assign a connection to the beam and the column here. I use the connection tool, selecting the primary member first, followed by the secondary member. Optionally, I can give it a name, and once I commit the connection is automatically created for me. The user, the coordinate system of the connection is automatically recognized, but the user has the option to adjust it if not desirable. Now, I've sped up the analysis process. It usually takes 1 or 2 minutes. But after the analysis, the user is presented with the connection design forces in the spreadsheets. So in 6 degrees of freedom, the demands are given to the user. Now, what's new in this feature is actually the ability to define connectors. It is possible to do this manually, as I mentioned. And in this case, all the information for the connector should be entered by the user. Now, in this case, I'm importing my connection from a connection database or connector database. So I can select which connectors I want to be imported. I can review them before importing into the model and make necessary changes if I want to. After it being imported, I can also review the properties of the connection, including the capacities, and I can adjust them if needed. And now I can go ahead and select my connection and assign a connector to the connection. Now that there is a connector assigned and it has a capacity, I can go ahead and run a code check. And now the results of the code check review is presented to me. I can see that my connection is passing in this case. And in addition to a high-level detail, all the details are given to me. This includes other requirement checks for the connection, including minimum required sizes of the members as well. As I mentioned, it's also possible to define connector databases as CSV files. So in this case, I'm opening a sample database that can be followed in order to make user-specified databases. And the last feature I want to talk about is new post-processing features for time history analysis. As you may know, time history analysis is a detailed analysis and includes results from many steps in the analysis. And it will be difficult for the user to interpret the results without the tools that we give them. So we have introduced 2 new features that help with post-processing of these results, starting with member envelope results, which gives the user a tool to understand the lower bound and upper bounds of the forces that the members undergo, as well as nodal plots for joint results, including displacement, velocity, and acceleration results. Now, in this model, I have a 4-story steel building that I want to run a time history analysis on. So this would have taken between 3 to 4 minutes to complete the analysis. And I can also animate my structure to review the initial response. Now, I want to focus on one member and understand the limits of the loads that that member undergoes. So now focusing on member 225, I could have given this member a name too. But here in this case, I can see that for the ground motion that we gave the building, the upper and lower bounds of the forces are given to me. And these are basically results from many steps in the analysis. So this is also presented to me in numerical format, which gives me an idea of which steps in the analysis caused the lowest and highest force conditions. Now, regarding the nodal result plots, if I focus on one joint now, which is node 116 in this case, I can go to my joint results, and I can plot the displacement, velocity, and acceleration results for the joint in question as well. So this information is also provided to me in a numerical format, which is handy when we want to have a detailed look at the results as well. All right, so now moving on to new features for STIL and SPAD. We'll now ask Siri to take on the presentation.
Thank you, Moin. So in the upcoming release of our steel design solutions, STIL will allow the design engineer to perform the design and code check of structural steel buildings under seismic load according to the current American seismic provision, AISC 341-16. The provision in this standard address one of the special and unique problems encountered within the full range of structural design practice. That is the design and construction of structural steel buildings, systems specifically detailed for seismic resistance. So central to the modern seismic or earthquake resistant design concept is the capacity design principle. So it is the design approach wherein the structure is configured and proportioned to restrict yielding and inelastic behavior to specific deformation control actions, for which structural detailing enables first, reliable inelastic response without critical strength decay, and through their plastic response, limit the demands on other portions of the structure such that those other parts can be designed with sufficient strength to reliably remain essentially elastic. So with this approach, the designer established which elements will yield and need to be ductile, and those which will not yield and will be designed with sufficient strength based on the forces imposed by yielding elements. So on the left, we have an S-frame models of 5-story buildings made of structural steels. When designing a structure under seismic load, the engineer will designate certain parts of the structure to act as a so-called seismic force resisting system, SFRS. So in the east-west direction, there are 4 concentric brace frames, CBFs, acting as SFRS, 2 in the front and 2 in the back there, as shown in the middle here. And in the north-south direction, 2 frames on the perimeter of the structure have been designed as SFRS. This type of frame is called a moment frame, as shown on the right here, where the connections between the beams and the columns are designed such that moments can be transferred between the 2 components. So in total, 7 types of SFRS in AISC 341 are supported in S-Steel as listed here. Essentially, there are 2 main systems, namely brace frames and moment frames with different levels of ductility associated with each frame type. And the one with special prefix such as the special moment frames, SMF, would require the highest ductility and thus more stringent detailing requirement than the ordinary or the intermediate one. And by detailing requirements, it means slenderness ratio or width to thickness ratio of certain members in the SFRS must meet the limits stipulated in the code. So if failed, such check will be reported in the code details for those members. For instance, as shown here, member 6, which is designated as a brace member in the brace frame, has slenderness ratio exceed the limit as required by the code. So this will give the design engineer an idea on how to improve his or her design to meet the code's requirement. For moment frame, S-Steel perform 2 additional checks that are not otherwise required for non-seismic requirements. This includes the column beam bending ratios and column panel zone shear checks. So for column beam bending ratio, the sum of the moment resistance of the column must be greater than the sum of the expected moment demands from the beams upon hinging or yielding in the beams. And for column panel zone shear check, shear in the panel zone, which are induced by the forces from the flange of the connected beam due to the bending moments, must be less than its shear resistance. And S still also calculates and report the probable resistance for the members that are supposed to yield under seismic loading, such as the beam in a moment frame or the brace in a brace frame. For instance, the RY in some of the formula represent the ratio of the expected yield stress to the specified yield stress Fy. So this ratio ranges between 1.1 to 1.6 depending on the steel grade. So essentially the code wants to make sure that the expected resistance of yielding members are calculated as realistically as possible, considering actual, not specified yield stress. So this information can be used in the analysis model when performing a nonlinear analysis in S-frame, which is required to determine the desired force for the non-yielding, or in the Canadian we call it capacity protected members. Recall those members that we don't want them to yield based on the capacity design principle. And let's look at how this works in S-frame. Okay, now I'm in S-frame. This is a model of four-story moment frame as part of SFRSS, seismic force resisting system. So let's assume that the beam have been designed and their sizes are known, and those for the columns have been estimated. So we want to get the proper design forces and moments for the columns, and then perform a core check according to the seismic provision in AISC 341. So the beams which are yielding members will be modeled by elastic plastic link beam element, the red one there, and the columns, the non-yielding members will be modeled by a conventional beam element. And for the beams at the first levels, the yielding or probable moment resistance was calculated as 1785 kilonewton meter, and to be sustained at this level after yielding. And similar setup have been done for beams at upper levels with smaller yield moment resistance. This one is 885, 826, and this one is 633 for the yield moment resistance. And for the load, there are 5 load cases predetermined. I have seismic, date, live, notional loads, snow loads. And for the seismic load, a scale of 3 is specified as an upper limit. And for the analysis, we can run either a nonlinear static or a quasi-static analysis for this purpose. And to keep it simple, let's run a nonlinear static analysis for 20 load increments with the include incremental results option checked. So I'm going to go ahead and run the analysis real quick. Okay. So we're in the graphical result windows here. Let me turn this off and look at bending moments. And so it turns out the structure becomes unstable after load step 10. Out of the total 20 load step, notice how the maximum bending moments in the beams at the first level have reached their U moment of 1785 kilo Newton meter, and also the upper is also have reached their U moment capacity. And if I right click at the jaw at the roof level and then select push over curve, which is a plot of displacement versus base shear, it is clear that the structure has gone beyond elastic range after load step 9 and become highly flexible after load step 10. So the force at this level will be used for the code check of the column in S2. So I'll going to S2 now. Yes, everything. And for the design codes that S2 supports seismic provision, currently the Canadian codes and the upcoming US code, the user is presented with this SFRSS tool. The members can be assigned their frame type, member type, and other related parameters using this tool. So for this model, if I will my frame type, it's already been assigned the SMF special moment frame to all the members. And I'm going to make sure that the member type is correct. The green one for the beams and the blue one for the column. And so now let's perform a code check for load step 10. Okay, so the columns on the left and right appear to have been properly sized with the demand capacity ratios or utilization ratios of around 0.8 to 1.0. And those in the middle are somewhat under design. To make them pass the check, however, there is another tool in S-Steel called user override section that we can also use for this. So let's focus on one column here at the first level and select it. And if I right click, this tool will bring this dialog box up. Note that member 13, the column with W610 by 341 section is selected. As the name suggests, this tool allows you to override the S-frame section with a larger or smaller steel section. And to make the member pass the check, I'm going to use the next size up option with do not auto unselect and assign it to the member until it passes the check. So I'm going to just 1 and 2. Notice how the ratio gets updated right away from the result of code checks being performed behind the scene for the override section. So after 2 sizes up, the column does pass the check. And before I conclude this session, I'd like to show you another feature called chart. So from the code details, if I click on the hyperlink for the section, and then short. I can use this function to plot the bending or compression capacity versus the length for several sections, say the S-frame section and the override section to see how they compare. Okay, this is the bending plot, and this is the compression plot. I also like to compare the two plots between the different design codes for a given section as a sanity check, if you will. So let's do New Zealand Euro code. How about Canadian code, Chinese, Indian, and yeah, here's my bending plot, and here's my compression plot. So they look comparable. So so we have covered a capacity design concept as it applies to the seismic provision in the US code, the seismic force resisting system, nonlinear analysis model setup, and Kojak in NetSteel. So that concludes my session. So I'll pass it on to Chris.
Okay, Siri, thank you. So we've kind of we've hit timber, we've hit steel. Now we're going to talk about concrete. As many of you know, with the concrete products, there are basically three products right now that are designing concrete elements, concrete members. Two are in what we call the classic line. One is in the new gen line, which is where S Timber lives, and S-Calc as well. So I just have one slide right now to present the updates for 2022.3. In S Concrete, we've had just some very minor updates related to things that weren't associated with named user licensing and those things, but those are included as well. In S-Line, we have implemented the CSA 19 code. The S-Line is just dealing with concrete beam members, so it's a smaller subset than S-Concrete, which deals with columns, beams, and walls. Also, in some cases, deals with seismic, particularly for walls. So a lot more effort going on in S-Concrete to be able to do that in comparison to S-Line. But be that as it may, we do have now 23.319 code support. There were a few minor enhancements and a couple resolved issues as well in S-Line. And then if I move to S Foundation, there have been some minor enhancements, a few resolved issues. With that, we've been working harder on the integration between analysis products. So S Foundation works as a standalone product where you can apply the loads or import loads, but it also works as an integrated tool with S-Frame and with ETABS. ETABS is CSI's kind of flagship building design software. And so that integration allows you to bring in an ETABS model that has no foundation elements, and you can instance the foundation elements and do the design on them. So I'm going to focus on S Foundation today, and really following the topic of design automation that Moeen sort of brought up for timber and for steel. Thought it would be also useful to see how S Foundation is sort of treating this. So this is an overview slide of S Foundation if you haven't been exposed to it before. And it is a foundation element analysis design and reinforcing layout software. So it's got its own built-in analysis engine, FE engine, meshing, force recovery, all of those things. It has the ability to do design by the code, and then also can draw reinforcing in 3 dimensions, which is very cool to be able to visualize that. So I won't go into all of the points of this, but we're going to focus on just one topic today with design automation. But just to give you an idea, S Foundation is I would say it's a true physical to analytical member modeling environment where the user manages the physical model. They specify the element type and what the dimensions are, what reinforcing, as a starting point, what material properties and those things, and then it creates the analysis model in order to perform its design. There are quite a few types of foundations that are supported right now, so it has a pretty wide range of tool set. We're going to focus today on this simple little isolated footing, but it also can do walls with strip footings. It can do a combined footing for columns. It can do a mat foundation that might have columns or walls on it. It can do a columns supported pile cap, so where you're dealing with the soil material as well as the concrete material in terms of design. And as I mentioned, the ability to draw the reinforcement is there, kind of parametrically defined in the environment. So our focus today is on this little footing that I wanted to kind of exploit what it really means to design foundation elements. And I think there's some really good features here that we could bring to bubble up to users and things like that through automation. One of the things that is important to understand about the new gen products, S Timber and S Calc and S Foundation, is they can be driven by Python scripts with their API. So that's kind of what we're going to be exposing here or exploiting here. But the topic today is this isolated footing. So if you haven't designed a footing before, it looks relatively straightforward, but it is fairly it has a complex set of rules that follow it, and you can also introduce the capacity of the soil and the stiffness of the soil, which make it required to be a kind of a finite element method approach. But it is the most widely used foundation element for most buildings, low and mid-rise buildings. It's fairly economical to construct, so it's kind of a low-tech thing. Put a pad, put some side forms in the ground, lay some rebar down and pour concrete in it, and then put your column on top of that. It can work for different types of soil as well as rock, if the rock is close to the bearing elevation. And so one of the nice things about the footing is that there is kind of a single path oriented workflow given a fixed set of input data, and I'll get to that in a moment. And the design code calculations, while complex or detailed, they are something that can easily be written computer to be able to manage. This particular model, which I'll show you in a moment on a live view when we go through this, I believe came from ETABS. I can't remember anymore if it's ETABS or S-Frame, but I've been working with it for a while. One of the other things that we can do is we can obviously put a mat foundation on the core area and go through the design for that as well. But today we're going to focus on the footing. And so the anatomy of an isolated footing and the design parameters that would come from this. So we have the soil properties, which is the bearing capacity of the soil and also the stiffness of the soil. That's represented by the subgrade modulus in the application. So that's this little screen on the right. We have a bearing capacity of 60,000 pounds per square foot. And we have a factor of safety of 3. I don't see where that's at here, but I believe that might be in the design. And so we're really working with ultimate loads that are reduced or calculate a factor of safety in terms of the design. We can specify the subgrade modulus of the soil as well. S Foundation has a number of different built-in soil layers that can be used or can be managed for different foundations. So it's got a pretty extensive soil library that allows these properties to be calculated for those things. And so in terms of the footing itself, we have length, width, and thickness, and we have the concrete strength of the footing. We have a pedestal sometimes when the footing is supported or it has to go deeper in order to get better bearing pressure. We might have to build a pedestal and then put the column on top of that. In other situations, the column could directly go on top of the footing. So we may have a pedestal that would have a size and a shape and a concrete strength. This screen or this little image shows the control over the pedestal. We can control its height, its shape, and its dimensions, and also the reinforcing in it. So we have kind of full control over that portion of it. The pad has a size again and a thickness. So a size and plan and thickness, and it's got reinforcement specification that the user can input as well. And so as I mentioned before, with codes right now, S Foundation is supporting the 31811 code and the CSA 04 code, also the Euro code. So in terms of design, there's, like you saw with Siri and S-Steel, and I think maybe Moini as well with Timber, one can do a code check, or there are some tools available at S Foundation through the scripting environment that are give you the ability to do the actual design. So that's kind of what I'm going to go through in this example for the footing. So these are the screens that the user would have for each of the 5 steps, components of the design. So the order of these, I'd say, are reasonably important because they kind of step through the logical reasoning that the user would have. There's not a lot of independency or interdependency of the different components. So, you know, we'd start by sizing the pad for the soil bearing, and then we size the pedestal to determine how big it needs to be on the pad. Obviously, it needs to fit on the pad, so the pad is going to be larger than the pedestal. And then we would size the pad for punching shear. There's 2 types of shear here. There's punching shear and there's one-way shear. Both of those are relying only on the thickness of the pad. So steps 3 and 4 are basically giving you the pad thickness, while step 1 is giving you the area of the pad. And then the last step is determine the reinforcement in the pad. In this case, it's flexural reinforcement that would be at the bottom or the top. For an isolated footing under vertical loads downward, it would be reinforcement on the bottom. And we have the different controls that the user has at the moment to be able to control the iterations. And it can iterate up to 30 steps in order to kind of come up with the most optimum design that meets the code check in this particular case. And so in a nutshell, this kind of goes through the process, and it kind of shows what the effect of each step is going to have. So we started with something that looks a little ridiculous, at least in my mind, maybe others not, but a small pad, a small pedestal with a relatively large column. And the first step is to come up with the size of the pad. So the pad grows from the original size to a larger size. And then in step 2, we grow the size of the pedestal in order to carry the vertical load and the moments that may be occurring. In step 3, we're growing the thickness of the pedestal. So 3 and 4 are combined here in the graphic. Those are checks for both the punching shear and the one-way shear. And then in step 5, we're looking at the reinforcement. to determine what bars need to be put into the pad in order to meet the flexural requirements. And then there's some reporting of the concrete quantities as well, and the reinforcement quantities that I think is an important part of an economical design. And there may be some opportunities to enhance those features as well. So before I go to this slide, let's go to the model. Maybe I won't go through everything, but so here's my model in S Foundation. And what I've done at this point is I've put 4 footings. They're all individual objects, so they all have individual IDs. This is footing number 1, and that's footing number 2, and then number 3 and number 4 is on the back side here. And so the reason I did that is so that the program knows that I'd like to look at all 4 of these individually and say, give me the size that's needed, even though some of the loads may be similar to that. Just a brief, just to show a little bit of. So this is the finite element representation of the footing. So they're mesh with a slab. The user does have control over the finite element mesh. So right now our pad mesh is only 2 feet. I'm going to change that to 1 foot. And what we're going to see is the pads remeshing based on that. So as their size changes, these parameters through the design iterations, these parameters will change or the mesh will update accordingly. And so what I, in the instance of time right now, what I like to do is I have the scripts that are exposed right now for the user are kind of in individual components, just like I showed in the screens. There's design pads to soil, design pedestals, design punching shear, one-way shear, and then flexure. So what, with a little help from one of our developers, we've now have Python script that exposes each one of those functions, and it also allows the user to set the parameters for each function. So basically what I'm doing here is I'm going to run all 5 of these at once, and I'm going to do it for a certain type of analysis. Flexible analysis is turned off, which means it's just going to do the rigid analysis. So let me just run the script. And let's say yes. And so now what it's going to do is, sorry about the screen flashing. That's something I need to see if we can get that to work. But hopefully you can see that the pads are being they're being increased. So this is sort of the automation part that the script is going through based on the rules that we've given it. It's doing the sizing of the pad. Now it's sizing the pedestal. So you can see the pedestal's getting larger. And then now it's looking at punching shear. So it's thickening the footings based on the punching shear requirements, trying to get them into shape. And I think the last part that's coming up will be the flexural. So now it's calculating the reinforcement, what would be in the pad required to meet the code checks. So when we talk about optimization in this sense, we're really talking at this point about the code check as a means of getting the results. And so what we see right now is we just see the last code check. But what I can do here, so I can see all of them, I can click save. And then let's run the code check for all of them. So this is the normal procedure that would be running for the user. So now we're going to run all of the checks at once, and we're going to get the results for all of them at once. And so now we can see our footings. And we could also see the finite element mesh has updated. It's a pretty clean mesh based on the size. So that's all been adapted. And we can also see the reinforcement in the both in the pier pedestal and in the footing itself in the pad. And if we wanted to look at the results, we can see the global results now. So this gives us an idea of how close we are. So the design method is, relatively efficient. We're quite close to the DCR, the utilization, and we haven't taught it yet that 1.0 still means pass, or at the very least, it means borderline. And but in any case, we have footings designed now for our building foundation with very little effort in terms of the user input. So that's the end of my portion. Thank you.